Okay. Now you could able to. Is the slide visible? Can I proceed?
Yes, sir.
Can I proceed, sir? Can I proceed? Slides are visible because I need a reply from moderator so that I can proceed further.
Slides are not visible. Sir, slides are not visible, sir.
No, sir. No, no, no.
Started sharing. So once, okay, just I'll do it again. I'll do it again. Sir. Now is it visible?
Okay, sir.
Yes.
Yes, sir. Yes, sir. PPT is visible.
Okay. Maybe moderator I can check in between if there is any delay in slide visibility. Please let me know. Okay.
Okay, sir. Sure.
Okay. So we'll proceed. So the topic which we are going to see in the second day of the session.
Sir, audio is not clear, sir.
There is future application of
Sir, audio is not clear, sir.
wait. Now is it fine, sir? Could you able to hear me now?
Yes, sir.
Okay. So this entire presentation is designed in such a way that how additive manufacturing will be useful for product development and what are the research activities or product development which are already there in market and some research activity what we have completed at VIT Vellore. And apart from that, we will see what are the recent application in product development through additive manufacturing process. So before to begin with the case studies and other product development activity, for next 10 minutes, those who are new for additive manufacturing, we will see what is additive manufacturing, how it is different from conventional manufacturing process. So if you look any manufacturing process, the manufacturing process can be broadly classified into three major categories. Some are formative process, subtractive process, and additive process. So formative process are you take a mold and inside the mold you pour a metal, powder, or liquid material, solidify it, and you get a final component. So these are example for formative process, example forging, powder metallurgy. Subtractive process, you take a raw material, using a tool you remove the scrap, as per the design you get a final part. The third technology is additive technology. That is, you take different thickness of material or different dimension of a material, you add according to the required shape. Example is welding. So any manufacturing process,
Sir, not audible, sir. Even though it is breaking, the voice is breaking in between.
so subtractive principle and okay. Now is it
Hello,
fine, sir?
sir.
Can I proceed?
Sir, some audio, I think audio is not clear, sir.
Sir,
That
I
is the
think there is
reason
a
I.
signal problem, the network signal problem.
Okay. Okay. So now, could you able to hear me properly?
Yes, sir. Now it's
Yeah,
okay,
now
sir.
it's okay.
Okay. Okay. In between, if there is a problem, please stop me, sir, so that I can wait for some time. Again, we will start. Okay.
Okay.
So these are three major category in which you can do the manufacturing process. Now, if you compare the subtractive and additive process, you have lot of advantage and disadvantage. For example, here we have to flow chart where you have to design a. This is a design. So this is the final part. You want to manufacture it, and the design is already completed. So now you want to make a you want to go for a manufacturing process. So here we have taken two scenario. The first scenario is a subtractive route. To manufacture this product, measure the maximum x-axis, maximum y-axis, maximum z-axis. Take a raw material. Using a machine, you drill the material, or you remove the material, you'll get a final component with wastage, because whatever you removed internally, it is going to be a scrap. In additive process, whatever the material you need, take it in a powder or liquid or filament form, deposit a material layer by layer as per the design, so that you could able to get a final component. Here the wastage is very less. So this shows the difference between the additive and subtractive process. In additive process, the wastage is very less compared to subtractive process. Suppose if you are dealing with very precious material, for example, this model I want to make it in gold. Anyhow, I can reuse it, but again I have to use some technology to reuse it. So the scrappage, the wastage of material is very less in additive process over conventional manufacturing process. So that is one critical advantage you have in additive process. Second, if you change a design, for example, I have a circular shape here. Instead of circular shape, I want to make it as an elliptical shape. So as per the design requirement, I want to change the circular shape into an elliptical shape. So if I want to change elliptical shape in additive process, I will be changing my CAD model. So the CAD model will reflect in layer by layer information. You can easily do the printing if you do any change. But in subtractive process, if you change a design, then you have to select a suitable fixture for that design. You have to select a suitable tool for this design. You may not use same tool or same drill bit for different shapes or for different design. So second critical advantage of additive over subtractive process is, if there is any change in design, additive is rapid in response. That is the reason additive process is also called as rapid manufacturing. So if there is any change in design, especially the topic deals with product design. So product design, when you design a product, it will go for a multiple iteration. So for multiple iteration, you should have a manufacturing system which can response immediately for different changes. So that is the reason why additive prototype or prototyping technology is majorly used in any product development industry. So though additive manufacturing is a recent terminology, the world name for additive manufacturing is rapid prototyping. That is, rapidly you could able to do a prototype of your product development, but those days it was only for a prototype. We cannot use it in end application. But with the advancement in control system, material processing technology, nowadays the prototype part is also used in end application. That is the reason why the additive prototyping, rapid prototyping technology is renamed as additive manufacturing process. Technology wise all are same. Layer by layer addition technology was there from 1980s onwards. But those days the technology was used only for prototype purpose. Why prototype? Because it is rapid in response for your change in design. So that is another critical advantage. You no need to worry about the tooling activity or planning activity for change in design. Now, if you look into the strength part, for example, if you have this two part, both are manufactured, one is by subtractive process, the other one is additive process. If I apply a tensile load, for example, you assume that I'll be applying a tensile load on the component. So same tensile load I will apply on the additive manufactured as well as subtractive. Definitely the subtractive process will give a better strength compared to additive process in terms of strength. The reason is, in subtractive process already the metal is solidified. You have a microstructure based mechanical property in a bulk manner that you are removing it, so you could able to achieve better strength. In this case, the microstructure and joining between layer by layer is done along the build direction, that is in z axis. So this is your x, this is your y, and in z axis. So along the z axis the interface will be there, and because of this interface the performance of additive manufactured component is less compared to subtractive process component. But again, with the advancement in technology, there are some report where the printed part or additive manufactured part is giving a superior behavior than the conventional manufactured part by using some in-process control mechanism as well as the post-treatment. That is, after printing, you do a thermomechanical treatment to enhance the strength of the part. So this is the major difference between the traditional manufacturing process and additive manufacturing process, and you all could able to understand how the additive manufacturing is unique compared to traditional manufacturing process. So there are different way in which you can add a material. I hope you all can see the animation. Maybe one of you can give a reply. I will proceed further. Could you all able to see the animation?
Yes, sir. Yes, sir.
Yes. So as I mentioned, there are different way in which you can add a material. An additive process will be adding a material, but the adding material can be done with different source of energy. For example, you can use a laser as shown in this you can use a laser, you can use a laser to join it, you can use a UV light to join it. So the raw material is also from different form. In some case it is powder, in some case it will be a solid filament, in some case it will be a liquid resin. You can see from this picture. So resin is swept. On the top of the resin you have a UV light, and this UV light will cure the contoured region. So though there are different level of additive process, different principle of additive process, to avoid any confusion, ASTM standard in the year 2010 have classified the additive manufacturing process into 7 major categories. So this category are based on the raw material as well as the source of energy to join. For example, VAT polymerization is UV based. Raw material is resin, and joining source is UV light. Material jetting, raw material is resin, joining source is UV light. So in both source is UV light, in both the raw metal is resin, but only thing is construction different. So material extrusion, the raw material is a plastic filament or metal filament, and and which will be extruded and melted layer by layer. So that is material extrusion technology. Binder jetting, a raw material is a powder, and using binder you are going to join the powder. Powder bed fusion, the raw material is powder, and using a laser you are going to join the powder. So in binder jetting and powder bed fusion, the raw material is powder, but in binder jet, the raw materials are joined by using a binder. In powder bed, the raw materials are joined by using a laser. Direct energy deposition, raw material is powder, as like the powder bed fusion. Only thing is construction. So powder bed fusion, direct energy deposition, source and raw material is same. The difference is construction. Similarly, vat polymerization and material jetting, source and raw material is same. The difference is construction. The another category is a sheet lamination, where you take a sheet, raw material is in the form of sheet, then using some mechanism you join the sheet layer by layer. So these are different type of technology. These are all different principle of additive technology, and each and everything has its own uniqueness. And because of the uniqueness, you can select the appropriate technology for a considered application. So as I have mentioned, these are all different commercial principle. Stereolithography, which is an vat polymerization principle, laminated object fraction, material jetting principle like polyjet, laser metal deposition is a DED principle. Binder jetting is a three-dimensional printing process. Powder bed fusion, again, it is like SLS and SLM. So this is the overall idea of how additive is different from traditional manufacturing process, and what are the different type of principles. So additive manufacturing or 3D printing, in the sense you should not confine yourself only with plastic or only with a toy model. You could also be able to make some workable aircraft or medical devices by using additive manufacturing process. So with this, we'll conclude the introduction part, that is about additive manufacturing and types of additive manufacturing. Let us all move into the next topic of our session, that is product development. So before we see some critical product development, let me give a glimpse of some innovative products which are developed through additive manufacturing process. And I will also give you the explanation why this product are feasible only through additive manufacturing process. For example, could you able to see the slide number 9? Slide number 9 is visible.
Yes, sir.
So here I have given few example where how only with additive manufacturing process we could able to develop such product. The first example is a fixation plate. You can see the metal implant which are kept over the bone, that is a jawbone. So this plate are called as fixation plate. Medically, it is a fixation plate. If you have a minor fracture in a jaw, to join the jaw, to align the align the bone and to repair the bone for healing, this fixation plates are used. This is a support, a man-made material. So though it is a medical application, definitely this has to be manufactured by some process, and mechanical engineer should involve in manufacturing of this part, right? So this fixation plate, what is the uniqueness? If you look into this fixation plate, the bottom surface which mate with the bone should have a same profile. If suppose the bone has this profile, the plate should also have this profile. So this profile I cannot measure by using any metrology equipment. I cannot use a vernier caliper or CMM to measure this because it is internal, right? So using some image processing technique, we could be able to capture the internal profile. So once you capture the internal profile, using a CT image, you can do a image processing to get a CAD model from the CT image. And from the CAD model, you can extract the surface, and that surface can be given thickness to develop a CAD model. right? So once the CAD model is ready, you can manufacture it. But in this case, it is manufactured through. So all the reference I have given at the bottom. So detail you can go through later. How, what is CT, MRI, what software used for processing, those things you can refer using this link. So this CAD model can be used to manufacture. In this case, additive manufacturing is used to manufacture. So layer by layer, once you prepare the CAD model, this will be sliced virtually. The CAD model will be sliced virtually, and that will be printed layer by layer to get a final component, right? So this can be done through a machined way also. You take a sheet or a plate, using a laser, you cut the profile and put a drill as per your requirement for fixation. You can fix it. So in both way it is possible, right? So in this case, it is a titanium material which is very difficult to machine through conventional manufacturing process. So we need some different type of processing technology. That is one case. That is, material is difficult to process. The second thing is, today I have a criticality like this. Tomorrow, some other patient may come and he may have a fracture here. And the same day, some other accident may come, they may have a fracture here, right? So I cannot say that all my customer required a same shape, because traditional manufacturing process will be helpful for mass manufacturing or in a batch manufacturing. But if you look into this, the medical case, it is an example for mass customized part. You need it in mass, but each and every part is unique. That is called mass customized production. You might have heard of batch production, mass production, and job production. Job production, each and everything is unique. There is no commonness between the part, and the time required for delivery is also high. Batch, there is a category. In each category, you have specific numbers. Mass, everything is same. But in this case, you need many numbers within a short period of time, and each number are unique. So in that case, additive manufacturing, since I mentioned initially, we do not have any tooling activity. There is no scrapping of material, and process is flexible to adopt for the change in design. So that is the reason most of the medical implant nowadays, they are preferring additive manufacturing. The reason is mass customization. So that is one critical application or product development where you can use additive manufacturing process. The another thing is topology optimization. I'll give our own case study which we have done in our college. So as of now, just I'll give what is I'll tell you what is synthetic feature. For example, if you look into the first design, it is a bracket used in aerospace component. In aircraft, it is a bracket used for some assembly. Now they have conducted a competition, and they asked us to the competition was to reduce the weight of the component. At the same time, it should withstand same load. For example, if you look into the first design and last design, both the design will withstand same load. For example, if I apply a load of 50 kilogram, first design as well as the last design will withstand 50 kilogram. Only thing is the weight of last design. If you look into if you measure the weight of last design, it will be less than that of first design. You can see visually also, you can see the lot of materials are removed. Here there is a material removal, here there is a material removal, here there is a material removal. So you can see some intricate cavity here also. So this material removal was done through a technology called topology optimization. Subsequent slide, I will be discussing about topology optimization. But as of now, there is a process which is next step to finite element analysis. In finite element analysis, you will be determining the material strength. You will be determining the factor of safety alone. You will assign different material. You try to identify the dimension which can withstand the load with a factor of safety. So that is what we are doing in finite element analysis. Beyond finite element analysis, you can do a topology optimization, where further you can reduce the material also. Apart from assigning the material, apart from deciding the thickness of a material, you can also reduce certain material to get a final component. So that is topology optimization. This was there for last 50 to 60 years. Topology optimization is not a new terminology. But most of the output from topology optimization is synthetic feature. So that is what I have given as a topic. Synthetic feature. If you look the first figure, shapes are very simple. You have a circular or a planar shape. So it is very easy to manufacture through conventional manufacturing process. If you look into the last diagram, you have lot of non-linear curves, a lot of non-linear surface, which is very difficult to manufacture. That is the reason why engineers are not comfortable to use topology optimization, because the issue is manufacturing constraint. This is very easy to manufacture, though the weight is higher than that of last design. It is simple to manufacture, but the last is, it can also withstand same strength. It can have a less material. Only difference is it has a lot of non-linear feature which is difficult to manufacture. As I mentioned initial, like in the first case, if you have a complex shapes, additive manufacturing doesn't have a constraint, so you can add a material layer by layer. And apart from that, if you reduce the material, again the cost of manufacturing will also decrease in additive manufacturing process. In conventional, you have to remove the material here, so that will be a scrap. So they do not want the scrap, or they want to avoid a scrap. So in both case, the additive manufacturing is suitable for synthetic feature. Another critical example is a gradient structure. So if you look into this figure, you have a splint for a fractured bone, like a medical case study. But within the model, you have a multiple material. For example, white color region is one material, black color region is another material, gray color region is another material. So if you have any fracture or misalignment in bone, instead of going for a cloth wounding as we do traditionally, you can go for this plastic splint, and this plastic splint is designed for this patient. You cannot use the same splint for another patient. And this plastic splint or rigidity of the splint is given in such a way that, as per the alignment, as per the fracture what you have, based on your CT investigation, the stiffness of the material is desired. So certain region you should not align, you should not allow movement. That is what we naturally do. If you have fraction, that should not, you should not allow the movement for better healing and for a proper alignment of a bone. So the rigidity of a material is arrived based upon the misalignment, and the contour is based upon the patient profile. And you have a flexibility in the material. You have, so black color region is very flexible, so you may not face any problem. If you provide the same flexibility at this place, then you may not have a proper stiffness. So this is another example where you can go for a customized product with a gradient material. The other important activity in additive manufacturing is the product development for electronic circuit. So we all know that different process used for electronic circuit manufacturing. One of the processes is the lithography process. In lithography process, what they will do, they will take a semiconductor wafer, they'll etch using a mask. Then in the etched region, they will apply a conductive paste. This will be repeated layer by layer. Finally, you'll be getting a electronic circuit device. So this is also similar to additive manufacturing, because in additive manufacturing also we are doing layer by layer. So the problem with the conventional lithography technique is, for each and every design, for example, the top region have a conductive pattern like this. In between you have lot of layers. You can see the layers which are visible in this figure. So this is also similar to additive manufacturing, because in additive manufacturing also we are doing layer by layer printing. And for each layer you have to prepare a mask. So instead of preparing a mask for each layer, and if there is any change in design, again you have to recreate a mask. Additive manufacturing, you can control using a CAD modeling process. Another critical example of additive manufacturing is integrated assembly, where devices are externally assembled. But here the printed process is integrated assembled. But here the printed process is integrated, refers from layer to layer, which is a technology which we have seen in the first slide, layer by layer additive manufacturing. So these are all some critical application of additive manufacturing, where you can develop a lot of product or innovative product using the layer by layer manufacturing process. And additive manufacturing is also one of the suitable process in smart manufacturing setup. So what is smart manufacturing? Traditional machine with some sensor, right? That is what referred as smart manufacturing. If you have a CNC lathe with automatic identification of tool wear, automatic identification of vibration, automatic identification of dimensional variation of a part. If you have some sensor and monitoring mechanism with a closed loop system, either it can be corrected by a robo or a manual interference, then that particular process is called smart manufacturing, right? So in additive manufacturing also you can do a smart manufacturing, but one uniqueness of additive manufacturing is in conventional manufacturing process you have a raw material. When you apply a smart manufacturing technique, you could able to apply the smart manufacturing concept only on processing of a material. You cannot apply the smart manufacturing concept on material microstructure itself, because material is already processed. You got a microstructure using some other technology. Only thing is the processing technology you are controlling. You are not controlling material microstructure. But in additive manufacturing process, if you look into the layer by layer addition, so each and every layer, whatever you are going to join or center it, it will be controlled by using a control system, smart manufacturing system. So microstructure is also controlled layer by layer, and mesostructure is also controlled for the entire component. So that is one critical uniqueness of additive manufacturing over traditional manufacturing. In traditional manufacturing, the smart application is either used in microstructure processing or material processing. But in additive manufacturing, as we process layer by layer, we could able to apply the control system or smart manufacturing application microstructure level at each layer, and also mesostructure level for the entire component. So that is one critical example where you can use or those who are interested in smart manufacturing or IoT, because nowadays any project proposal or project component from industries always required a IoT association into the project component. So additive manufacturing is one of the suitable example where you can do a IoT application for material processing as well as the microstructure control. So that is another uniqueness of additive manufacturing for smart application. The other important application of additive manufacturing is repair application. For example, you have a component which got weared or tear over a period of time. What generally they used to do, they will cut a weird region and they will take another bulk material and weld it, right? So again it will have an interface because you are doing a welding. If there is any damage in a part in the application, you cut a part and take a bulk material, weld it. So that is one type of repair application for high-end material. But again you have an interface between the added new material and the old material. So instead of that, what you can do is you cut a weird part, take a measurement of a weird part, that is wear surface. From the wear surface you create a CAD model. Once you do a measurement, you get a basic surface. From the basic surface you sketch a part in a CAD software. That software model you transfer to the machine. So machine will deposit a material layer by layer from where it got weird. So you could able to get a end part. Now what is the uniqueness? In a traditional repairing process, you are going to replace the weird material as a bulk material. Whereas in additive process, you are not going to add as a bulk material, you can gradually add it. Because of a wear, because of the thermomechanical effect, you may have some constituent alloy in the weird region also. So this can also be controlled layer by layer. So this is another reason application where you can use additive manufacturing. Cladding is already there. Cladding is one process where you can do for repair application. But in cladding, we are not controlling in a three-dimensional manner. So additive manufacturing is extension of laser cladding, where you could able to control the shape in three-dimensional manner. So as like a bulk interface, you could able to avoid and gradually change a material property layer by layer through additive manufacturing process. So these are all some critical example for additive manufacturing and product development used in additive manufacturing. And you could also able to understand why only in additive manufacturing you could able to achieve the better functionality. So next few slides, I would like to share some case studies which we have done in our campus. So as I mentioned initially, could you all able to see slide number 13? Slide number 13 is visible.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
So as I mentioned earlier, there is a component called the topology optimization. Since the workshop focus on uh, product development, I feel this topic is very much useful for design engineer as well as for manufacturing engineers. So uh, there is a terminology called topology optimization. So what does this topology optimization will do? Maybe with this diagram I will explain. So you have a initial geometry. So you have initial geometry. So this is a CAD model of the geometry. This part is already used in end application. You do not have any problem in end application. Already this model is designed, material is assigned, geometry are finalized with considering your factor of safety. There is no problem. This is perfectly fine, right? So this model you got it through analysis. After CAD, you do a finite element analysis and check whether the factor of safety is within the limit. If that is there, this design is finalized. You can go for manufacturing. Right now, what this topology optimization will do? The topology optimization will give same factor of safety for a same material, but in addition to that, it will also remove some material. For example, you can look at the bottom. So this is the topology optimized structure for the initial geometry. So you can all able to see the difference. In this case, it is a bulk material. You have lot of perforated holes. Both will withstand same load. Both are made of same material, but the final geometry after optimization will have less weight. Why do you want to reduce less weight? Because in aerospace application, especially if you take aerospace application, even if you reduce 1 gram of material, it is appreciable, right? So that is the reason topology optimization is very critical in aerospace application. So topology optimization helps you to reduce the material without affecting your functionality. So how to do that? You have to create a FEA, same FEA model, and apply the boundary condition and do the analysis. You will get the results like this. So this is the topology optimized model. This is the finite element model for your design. Now, if you look here, there are some region which are red, right? There are some region which are in blue color. So what does this inference? The red color region is a high stress region. The blue region is a low stress region, right? So within the model, there are some region which has less stress. There are some region which having less stress. I hope you all can understand the FEA results, right? So factor of safety is determined based on red color. For example, if I assume the factor of safety is 2 and material yield strength is 200 megapascal, then the red color region will have a stress of 100 megapascal. Then it is factor of safety is 2. If the red color region itself 100 megapascal, then obviously the blue color region will be having a stress of 50 megapascal. Right. So what is the factor of safety of blue color region? It is 4. The factor of safety of red color region is 2. When we do a finite element analysis, we will be considering only the maximum stress region. And based on the maximum stress region, we will say, yes, this is the maximum factor of safety. But your end application is fine if you have a factor of safety only with 2. But there are certain region where the factor of safety is 4. So what you can do, you can submit the FEA results to a topology optimization. So there is a model called ATOM, that is the topology optimization model. What it will do is, the topology optimization model will read the stress value for each and every element, because in finite element analysis we will be doing mesh. So each mesh will have a stress value, and you have to tell if the stress value is, for example, here the stress value is 100 megapascal. So if the stress value is less than 75 megapascal, automatically you can remove the pixel, or automatically you can remove the element. That particular element will be removed. So as already the FEA model is element model, it will have a stress value for each and every element, whatever the threshold value. For example, in this case I say 75 megapascal. So whatever the element, that is one way of doing optimization. You can also tell to the software that reduce 30 percentage of material. So it will see, it will it will arrange the element stress value from ascending order or descending order. From the bottom, it will reduce the element until it achieves 30 percentage. Sometime you cannot achieve in single iteration, you have to go for multiple iteration. You can also reduce the material by using a stiffness, because I cannot go for very thin region at the contour, right? So always at the outer edge I should have some material compared to inner edge. So based on stiffness also you can define a topology optimization. So that is the importance of topology optimization. It will read the element property, and it will decide the requirement of element based on your threshold value, and it will remove that particular element. So finally you could able to achieve the shape. This shape might be irregular, so you can smoothen the shape, because as the element are removed randomly, it will remove, so you may have lot of irregular feature. So that will be very difficult for manufacturing. So smoothen it by using some algorithm, then you will get a final component. So this component is a optimized component, and the factor of safety is same as that of original model. If the original model is around 2 kg, then the optimized, just example I'm giving, if the original model weight is 2 kg, the optimized model around will be around 1.5, or in this case let us take 1 kg. So almost 50% reduction in weight, but it withstand the same load and there is no change in material. So that is the critical application of topology optimization. I didn't talk about additive manufacturing, right? Why additive manufacturing is having a major impact on topology optimization? If you take the first, let us take, this is the first model, and this is the second model, topology optimization. So which is easy to manufacture? Forget about additive manufacturing. You take conventional manufacturing, machining process. If you look into the first diagram, you take a sheet metal, cut a sheet metal, join it. It is very easy, right? In this case, you have to, because you need the exact dimension. If you simply add a bulk material, then there is no use of topology optimization. So wherever the material is shown in the model, only on that region, only for that dimension, you have to add a material. So it involves lot of intricacy. Even if you do a machining, this can be milled. But here the milling is very difficult. You need different tool to mill. This has different intricacy. Sometimes this can be done in a 3-axis VMC. For this component you have to, because only 2D view I have shown here. This diagram you can see the 3D intricate shapes. Internally you have to groove a material. So that is the reason engineers have not thought of topology optimization for conventional manufacturing, because topology optimization helps you to reduce the weight, but at the same time it will give a lot of problem in terms of manufacturing. But if you take additive manufacturing process, as add a material layer by layer, irrespective of complexity in shape, because in additive manufacturing process, complex shapes is not at all an issue. You are going to divide a complex 3D model into 2D layers, and layer by layer you are going to add a material. So complexity is not at all issue in additive manufacturing process, but still material consumption is also less. For example, if I manufacture a same component using additive, you have to spread lot of material, you have to spend lot of material. But in this case, manufacturing material consumption is also less, weight of the component is also less, and there is no issue in intricacy to certain extent. Still there are some issue, you cannot go for very complex shapes, but to certain level. If you study in deep about design for additive manufacturing principle, there is also some restriction. So if it is within that restriction, you could able to achieve the topology optimized component. So let me show one case study where our undergraduate student used this topology optimization. So this is a part for this robot, a small mini robot for industrial application, and this robot has to used for palletizing operation. It has to hold this component for palletizing and depalletizing. So you all can see the gripper here, white color material. So now this component have a certain, I cannot use a flat gripper. So as per the profile of the component, circular feature, I need a end effector shape, because end effector should have a negative shape of your component. So that is the reason why the particular application, this is the end effector which come along with the machine. So this is the internal shape, and this shape should be as per the profile of a component. So for that reason, they went for additive manufacturing, because as per the shape, they want to immediately create a plastic component. So they started with the CAD model, and they have converted a CAD model into a mesh model, FEA mesh model. Then based on the robot, because this two hole is used for fastener, so the boundary condition is applied, and we know the load of a component which we are going to pick and place. So that load is applied on the surface, and we got the contour plot. If you look into the contour plot, only here you have a stress. Only in this region you have a high stress. So it is within the factor of safety. But if you look into the other part, you have a lot of blue color region where the factor of safety is very less, right? So this we have taken it for topology optimization, multiple iteration we have performed. So here, for example, the constraint I have given is retain 70% of volume. So this is the result for 70%. Retain 50% of volume. Retain 25% of volume. So we got different results. So if you look here in this diagram, this is another issue in topology optimization. You have an island feature. So there is no connectivity, there is no meaning, because you should have two hole. So this has to be rectified by using a shape optimization. Later you can create a sketch to join the first circle with another circle. Why it removed? Because I have given very high volume constraint. I instructed the optimization software to retain only 25% of original material. So this is the original volume. So volumetric constraint is given. So based on the mission, again, after optimization, I have to see whether the mission has a capability to manufacture, because this shape is very complex. So additive manufacturing is used to manufacture the shape. But again, if you look into the future, in 25%, we got very thin region here. So this thin region is very difficult to manufacture through additive manufacturing. Facility what we have, maybe some other facility might be useful. So based on the manufacturing constraint and optimization constraint, 50% model is further taken for shape optimization. We have added some additional feature for connectivity, and that have been manufactured. So if you look original model using FDM additive manufacturing process, the time required for printing is 27 minutes. Optimized model, the time required for manufacturing is 21 minutes. Material consumption, that is, it is a filament based process. So maybe we can see one. Maybe we can see the FDM process if you are. So you could able to, you could is visible. Could you able to see the video? Video is visible to all.
Yes, sir, it is visible.
Okay. So this video is for those who are not know about additive manufacturing. This is a simple 3D additive manufacturing process based on FDM. So similar process we have used for that part, which I have shown here.
Manufacturing process.
So this will have a nozzle. Two nozzle is there. So one is for part, another is for support. You can also use multiple material.
Is production-grade thermoplastic materials to produce both prototype and end-use parts. This technology is known to accurately produce feature details and has an excellent strength-to-weight ratio. FDM is ideal for concept models, functional prototypes, manufacturing aids, low-volume end-use parts. The FDM process begins by slicing 3D CAD data into layers. Data is then transferred to a machine.
So the raw materials will be loaded as a filament. So filament is shown at the bottom.
Part layer by layer upon a build platform.
So this filament will be pulled into the nozzle head. So this is the nozzle head. You can see the nozzle head. Nozzle head will have a heater. Because the filament is in solid form, you have to melt the filament for easy flowable condition as per the CAD model. So the nozzle will have a heater. So this filament will be pulled.
And support material are used to create each cross
So in this case, two materials are used. Some machine will come with a single material.
section of the part. Similar to a hot melt.
So this is the nozzle, which is very critical part of every machine. So this nozzle will have a heating coil and roller. Roller will rotate on opposite direction to pull the filament.
Slowly extruded to jewel.
So you already have a CAD model. So using a data processing software, the CAD model will be sliced into n number of contour. So for each contour, as per the contour and the internal cavity will be filled layer by layer. So once one layer is done, the table will go down and next layer will start to print. So this is what I have mentioned. The same machine can be used for turbine blade, and tomorrow you can manufacture medical implant, plastic devices. And day after tomorrow you can print the architecture model. So there is no limitation in terms of variation in design.
Move in a horizontal XY plane while the build
So layer by layer, the table will go destroyed.
parts have visible layer lines.
So kindly apologies to those who know about the technology. It may not be new to you. This is for those who are new to the technology. So I hope now slides are visible. Slide number 21.
Excuse me, sir, the slides are visible, but I think there is one of the participant whose mic is on. So it's not clear when you
Yes,
speak.
maybe the moderator can mute the participant.
Yeah, it's done, sir. Thank you. You can continue, sir.
Okay, now my voice is audible.
Yes, sir.
Thanks.
Yes, sir.
So that is about the time of printing. As we print layer by layer, you can see the time difference. This is an optimized model. 6 minutes, but you think of mass production, more than the mass production, change in design can be immediately adopted. As I mentioned in the video, the raw material will come in the form of filament. So the length of material is 2.5. It is material consumption. It is 2.5 centimeter cube, and here it is 1.8 centimeter cube. Cost of printing based on the material and the time of printing, the cost will be calculated for the machine what we have taken. So you can see the difference in terms of production, and we could also able to achieve for different. For example, tomorrow using the same robot, the manufacturer want to pick and place a egg, or he want to pick and place a carrot, and as per the carrot, again we can rechange a design and optimize the design to reduce the material cost and printing cost. You can rapidly implement in your end application. So that is what one of the unique application. Maybe the detail of this paper is given in the link. So the link is also given in the presentation. So those who are interested in topology optimization, this is one critical example where you can see how the additive manufacturing can be coupled with topology optimization for rapid product development. And another important point which you all should understand here is we are making the component very complex, and this complexity for enhancing the functionality. So you increase the complexity, reduce the cost, and enhance the functionality. So I hope with this case study you all could able to understand the impact of additive manufacturing for such product development. I thank the organizer for giving the opportunity. Thank you. Yes. Yes, I hope, yeah, exactly it is 12. If there is any question, I can take.
Good afternoon, sir. I have one question. Is there
Yes.
any possibility to implement topology optimization in metal-based additive manufacturing techniques?
Yes, the first case study which I have mentioned for aerospace bracket, it is a metal case study application. But only thing through this session I want to convey here is, even in topology optimization, you cannot go for very complex, intricate shape. There is a restriction. So those who want to use topology optimization with additive manufacturing, I kindly advise you to go through the design rules. As Professor Sadish asked, it is always better to see the design rule for metal additive manufacturing process. It is feasible to do a topology optimization for a metal process, but the constraints are more in metal than the plastic.
Sir, what is the usage of OptiStruct software, sir, in topology optimization?
Yeah, see, topology optimization is used for reducing a material. There is also another way to reduce a material. That is, instead of having a solid material, you make it as a cellular material. You don't do topology optimization. Just convert a solid material into multiple cells, connected cells. So OptiStruct is one software where you can convert the solid design into a connected cellular structure. So if you have a cellular structure will have a dimension, it will have a thickness, it will have number of cell. So those designs can be optimized using OptiStruct application, where you can combine the cellular structure with additive manufacturing. Slides, yes, any other questions, sir?
Thank you, sir.
Thank you.
Excuse me, sir. How do you
Yes,
feel the adaptation of additive manufacturing is being done within the Indian manufacturing sector or within the SMEs? I mean, majorly asking about focusing on small and medium enterprises. How do you feel the adaptation is being done with regards to the additive manufacturing?
yes, sir. Thank you, sir. So, based on my interaction with some of the SME, they started to adopt additive manufacturing for tooling activity, especially in molding, as also for sand casting pattern. So in SME, for tooling, there is a lot of reach, and there are a lot of need for tooling activity through additive manufacturing process. Especially in my slide also, I have one more example which I didn't share. There is an application for conformal cooling channel. So in tooling, you need a uniform solidification. So conforming cooling channel is one critical example where I can see a lot of original equipment manufacturers also used additive manufacturing to make a tool with a conformal cooling channel. And now, instead of procuring our own individual facility, a lot of centers are established in Chennai, Bangalore, and Pune. So it is not necessary that always the company should own a 3D printing process. Instead of that, there are nodal centers from government as well as from private organizers, and in some academic institute also they have metal as well as plastic institute. So instead of procuring a machine for a SME, it is always advisable to get a help from nodal center, and this is already happening, especially in tooling activity.
Okay, thank you, sir.
And medical application, there are a lot of scope. Some hospitals, they have demonstrated the case study. And some doctors still they are procuring from outside, and they may not be aware that it is processed through additive manufacturing process. So we need a lot of interdisciplinary research from or interdisciplinary activity combined with hospital and academia or hospital with industry for medical.
With regards to the medical equipment,
Yeah.
are they procuring internationally, or even the materials are available in India itself? Or
No, because the approval and processing of a material needs certain accreditation. So whatever the case study I came across, all are procured from outside.
I mean, you the outside, you mean internationally, right?
Internationally, especially from Germany.
Okay,
Only thing is we need to follow proper accreditation process. If you procure a machine or if you have a machine, make sure that you follow the standard as per the medical implant guidelines, and that has to be accredited by Indian system also. Then we can think of feasibility of manufacturing indigenous implant. I haven't come across any case study where they procured directly from India.
Okay, so it means that there are no readily available materials or manufacturers to produce that.
No, manufacturers are there. Manufacturers and materials are there, but only thing is accreditation. Because, for example, if you procure a metal machine for implant, if you are fabricating a material, particular material, for example, grade 5 titanium, and immediately there might be another requirement from tooling industry where they need aluminum, or they need some stainless steel. So if you change a material, again, the chance of contamination, or you have to make sure that there is no contamination, and you have to follow the proper protocol. So that is very critical. So there should be an exclusive center with the accredited body for medical implant supply.
Okay. All right.
Thank you. Again, for the question for Sarath, in other than implant, external devices like prosthetics, there are a lot of supports available in India. Prosthetics.
Yeah, because prosthetic, I don't think they need much
external contact.
Right?
External contact, it is already there.
Okay, for the internal, there are no much contractors who can produce the material due to those approvals, right?
Yes.
That's what you meant.
Yeah, that's okay.
All right, thank you.
Hello, sir. Hello.
Yes, Jitin.
Sir, I have a doubt that in the sixth slide you have mentioned some processes are indirect method and some as direct method. So can you explain that? Because I couldn't get.
I think, can I share the slides?
The sixth slide. Slide number 6.
Okay. So could you able to see the sixth slide?
Yeah, now it is coming.
Internal and external, right?
Yeah.
Okay. So no, here I did try to mean. Yes, maybe other participants can mute. So here it is based on the construction. For example, if you take the powder bed fusion and direct energy deposition, so these are all two processes where it uses a laser. DED is also using a laser. Powder bed fusion use a powder material. DED also use a powder material. But if you look into the powder bed fusion, the powder will be swept from the adjacent table. And using laser, you are joining the powder. If you look into the direct energy deposition, there is no activity of sweeping. The nozzle is very unique. It is a coaxial nozzle, as we are using in cladding process. So this coaxial nozzle will have a laser, and to the circumference of the laser, there is multiple channels. These channels will feed a powder. So that is the construction, internal and external construction. So because of this construction, in DED process, you can control the composition of material at the time of printing. Because as it is fed from the external cavity, you can control the feeding composition and you can control the feeding material also. But in powder bed fusion process, already the material is there. So if there is one material or one composition, only from that particular material and composition, you could able to get a final part. So that is what I try to mean in terms of construction. There is a difference. So though the principle and raw material is same, because of construction you are getting different uniqueness and advantage.
Sir, my doubt is that in the bottom you have mentioned the first three processes as
Okay, sorry.
metal indirect.
Okay. Okay, thank you. So I didn't explain this part. Thanks for reporting this. Metal part indirectly and directly. That is, this four parts which I have mentioned. This parts directly you can do a metal printing. If you need a metal component, directly you can create a metal component. Sometime there may be a question, sir. I have lot of advantage. For example, if you take VAT polymerization, it is resin based process. I could able to get very high finish, but I cannot process metal through VAT polymerization. I cannot process metal through FDM, because in FDM mostly plastics are used. So I need cost of FDM is less, but I can make only plastic component. I need less cost, high finish, but with metal. So researchers have started to explore this technology also for metal. So directly you will not be getting a metal core. So if you take in this case, they will combine them like composites. In composites, we are mixing resin with ceramic, right? So there are some cases where they have combined embedded particle into the resin. So they will get a printed part, which is a combination of resin and metal embedded particle. Some case even ceramic particles also. Later you do some post processing. You do some curing or curing or post processing. You could able to get a metal part. So that is a thing I have mentioned here. Metal parts indirectly. It doesn't mean that I cannot make metal part through FDM. FDM material extrusion also support metal part. So there are some cases where fused filament fabrication, where metal extrusion filament fabrication, where metal is extruded layer by layer, metal filament is extruded layer by layer, and later you have to do some post process to get a better part. So that is what I have mentioned here. Indirectly, you can also get a metal part through this process also.
Okay, sir. Thank you, sir. One more doubt.
Yes.
Recently, we are hearing that the KFC, Kentucky Fried Chicken, is planning to print 3D meat chicken nuggets. So, is there any similarity between what we have discussed here with
No,
that
no,
bioprinting?
I didn't get your question.
The bioprinting. Recently, we are hearing that bioprinting process. KFC is trying to print chicken parts uh, as a 3D
Okay,
printing. So, is there any connection with the bioprinting as well as the 3D printing which we have already discussed?
Okay, and maybe I can take from my institute case study also. In our institute also, we have recently procured one bioprinting for printing tissues. So there is no matured development in bioprinting, but machines are available. Even in India, machines are available. In my own institution, we have one bioprinting where researchers started to print tissues, and they started to explore the printing of organ also, but it is not in matured level, but the technology is there in India also.
Okay, in that case, in biological parts means it should have life or just
Yeah,
without life.
you have to print the tissues or cells, whatever you have, in an incubated manner, bioreactor.
Okay, so that can be used for like organ transplantation and all those things.
Yeah, it
Is it
can
all?
be. It can be. It can be. It is not in matured stage, but researchers are there. Missions also there in India. Also, we have a lot of missions. Skin, they have demonstrated skin prosthetics, skin patches for if there is any wound or scar. For skin level, reports are available, but not in organ level.
Okay, I think in the near future
Near
we may
future,
be able to
see, only
print
thing
heart.
we need interdisciplinary researchers. So with mechanical engineering alone we could not able to make. We need a instrumentation people for mission development, and as well as the biotechnologist for interdisciplinary activity. In near future it is feasible, sir. And research, a lot of research is also going on in our country. Also research is also going on for bioprinting activity.
Okay, sir. Thank you.
Thank you. Yes.
Excuse me, sir. You were talking about that there is additive manufacturing, 3D printing that is available for the, for the skin and all. And I would like to know with regards to the price feasibility, because if we take the case of a person who is getting fired,
Okay.
there will be a requirement for the skin to be attached,
Okay.
and there is a method that, like fish skin is being used. And now, as a part of the additive manufacturing, we have the skin that is produced by 3D printing. So, what do you feel, or have you seen any case studies with regards to the price feasibility of these two materials?
No, price.
And how do you feel?
Price feasibility of entire that is outcome, the entire product, or mission price you are discussing, sir?
Both, because it depends
No,
upon the
okay.
entire mission will depends upon the price of the skin where we do it, right?
Okay, so regarding the entire outcome or entire output, I do not have any idea. But if you look into the mission, maybe for others also it will be useful. There is a technology called aerogel technology, right? So using the aerogel technology or another technology is called direct write technology. So these two are the technologies which are so far used for this bioprinting process. And if you look into this technology, again, the cost of the machine range from 1.5 lakh to 2 crore from market, whatever I have understood. Again, it depends upon the setup, what you have, and resolution, because in certain case you need very high resolution. So the resolution range from microns to 0.5 mm. So the resolution of the machine is also very critical. So regarding the outcome, I do not have any idea. But with respect to the technology, this is what the status. Aerogel, if you are interested, you kindly go through about the aerogel based bioprinting. And
Sure,
this
sir.
price range from 1.5 lakhs to 2 crore.
Okay. Thank you, sir. Thank you very much.
Any other questions?
Is that, there is one more question. What is the clear meaning of threshold value in machining process? I didn't understand. In machining process, the threshold value is for optimization. You can give a threshold based upon volume, how many percentage of volume you have to retain, or based upon the stress value, or it can also be based upon stiffness value. So that is the threshold for optimization. How to select a material for rapid manufacturing? The problem with rapid manufacturing or additive manufacturing process is material constraint process. We do not have a flexibility for choosing wide range of material. And if you look into certain additive manufacturing process, you have to procure material only from the machine manufacturer. If you procure a machine from a particular manufacturer, you have to procure a material also from particular manufacturer. So again, if you look into the material catalog, we do not have much variety of material. The reason behind this restriction is rapid melting and rapid solidification, as I have shown in control monitoring. You need lot of parameters to be controlled for rapid cooling, melting, and solidification. So that is another scope of research. If you are interested in material processing for layer by layer manufacturing process is also a scope for research.
So good morning, sir.
Yes, Nagaraj.
Yes, how additive manufacturing improve in the product life cycle management, sir?
Okay, thanks for the question. The importance of additive manufacturing is it is rapid in terms of change in design. If you change a design, you could able to rapidly make a physical component of changed design in prototyping activity. So that is one critical component where prototyping activity already it is matured. instead of manually crafting the prototype, what you have concept or what CAD model you have, you can do a real component, physical component rapidly. That is one part, rapid response to change in design in prototyping activities. The second part is tooling activity. For example, after manufacturing, if you go for a tooling condition, anyhow you have to go for some tool. Other than the welding process, you have to make a tool. If it is a molding or powder metallurgy or casting process, you require a pattern. So in that case, your design is finalized, but instead of going for a mass production, you want to make a component in few quantity. Your requirement is only 20. So there is a technique called soft tooling. Instead of manufacturing a tool at harder material where the machining is also difficult and cost of machining material cost is also very high, in that case you can go for a soft tooling. So in manufacturing aspect, through a soft tooling, additive manufacturing is already in place, as you have mentioned in product life cycle. Again, one more application in product life cycle is repair application. If you go to GE Additive website, GE have had their own division called GE Additive. If you click GE Additive, the first case study is how they are using additive manufacturing for wear and damaged aircraft turbine blade. So in turbine blade, it is a unique processed material. So if there is any wear or damage after a period of time, this repair and refurbishment is another activity which you can use additive manufacturing in your product life cycle. So these three are already there in case study. And apart from that, as I mentioned, if you need high functionality, high complexity without affecting the cost, then additive is one suitable technology. Thank you.
Thank you, sir.
Thank you. Yes, I think.
Sir, I think there is some questions in the chat.
Yes, sir. I am reading from chat. What is the feasible of printing functionally graded materials for nanotube? As I mentioned in the direct and indirect method, in indirect method, you can print. You cannot directly print a nano material. Case studies papers are available where you can mix a nano material with a resin, and that resin you can process using a UV curing like we do in composite material. You could able to get a 3D part, and internally you will have a embedded nanoparticle. But the difficulty here is what kind of interface developed between the nanotube and the UV light, that has to be investigated. So it depends upon the end application what you are looking for. So that is a drawback we have, but processing is feasible through indirect method. You mix powder with the nanomaterial, studies are available, or mix a resin with a nanomaterial using a stereolithography process. And you can, a functionally graded material is very important. A functionally graded material for nanotube. You cannot make a functionally graded nanotube, but you can distribute the volumetric percentage of nanotube from one layer to another layer. That is feasible. Like as I mentioned in DED process, you can gradually, for example, if you are feeding a material, material have a composition of alloy, from layer by layer without affecting the interface bonding, you can explore the chance of varying the composition from layer by layer. So that will help you to give a nano material. So that is also another important area of research of for functionally graded materials. So Ruben, what is the feasible of printing? Okay, so carbon nanotube. So that is okay, sir. I think I have answered all the question. If I have missed anything, please raise me.
Is there any other questions? Respected Dr. Sugavaneswaran friends, the session delivered by Dr. Sugavaneswaran was exploring to the details of new trends in industry, and it was really enriching. The concepts of course inspired us. I take this opportunity to express our gratitude to the resource person. As a token of love and gratitude, I request this eminent personality to accept our sincere words of thank you. Thank you, dear sir.
Thank
Also,
you,
we
sir.
express a word of thank you to all the delegates of this session. Thank you very much.
Thank you. Thank the
Tomorrow's session
head
will
of
be
the
handled by
department and the
Dr.
organizer.
Tom Matthew from School of Mechanical Engineering, VIT Vellore at 11 a.m. Thank you all.
Okay, thank you all. Thank you, participants. Thank the organizer for giving this opportunity. Thank you.
Sir,
Yes.
yeah, if there are any questions, means shall I mail you, sir?
Yeah, you can mail. My contact details are available with the organization. You can mail. Thank you.
Yeah, sure, sir. Thank you, sir.
Thank you, sir. Thank you.